So in this lesson, we're going to be considering standing waves in air columns or pipes. So by the end of this lesson, you'll be able to calculate the resonant length for different types of pipe, be they open at both ends like this one, or closed at one end and open at the other. And you'll also know how to account for end effects. You'll then apply this to an investigation where you'll use these standing waves, the resonances that you hear, to measure the speed of sound in air. So this is relevant to musical instruments, as wind instruments such as recorders, clarinets and flutes all make use of standing waves in order to make the nice notes that we can hear. Standing waves in air columns are very similar to standing waves on strings. In strings we had an input wave which was reflected from one end, and then we got interference between that input wave and the reflected wave, which led to the standing wave. Exactly the same thing happens in pipes. Now this is quite obvious when we've got a closed end. We can have an input wave here and it's reflected off this closed end here, and we get standing waves set up. Remember, a difference with sound waves is that they're longitudinal waves, so in this case the particles are moving backwards and forwards like that in the parallel to the direction that the wave's travelling. It's less obvious why we get the reflection occurring off an open end. One way to think about this is that to the sound that's propagating along, the medium where it's confined in the pipe looks quite different to the medium outside the end of the pipe here, where it's free to move out in all three dimensions. And so when it comes to the end of the pipe, it sees a different medium. And we've seen that when a wave goes from one medium to another, some of it's transmitted and some of it is reflected. So that's exactly what happens with open pipes. If we played a note here, some of the note would be transmitted and continue going this way, but some of it would also be reflected back down the pipe from this open end here. And so that will set up a standing wave, which, if it's harmonic, we'll learn about this in a minute, you can actually hear. We'll start by considering pipes that are closed at one end and open at the other. Pipes have a node at a closed end. This makes sense because the particles can't move backwards and forwards like this if they're stopped by the end here. So we have a displacement node at the closed end, and we have a displacement antinode, which means the displacement is the maximum value at the open end. So the first harmonic, or the fundamental frequency for the pipe, is the longest wavelength for which we're going to get a resonance. Now that will occur when we have an antinode here and a node here. So in this diagram, you can see that that'll happen when we have a quarter of a wavelength inside the pipe. So remember, as with standing waves on strings, one loop is equal to half a wavelength. In one wavelength, we've got the two loops. So what you can see here is half a loop, so that's quarter of a wavelength. So in this case, we're letting the pipe have length L, and the L is equal to quarter of a wavelength. And so we can work out the fundamental frequency of this pipe. If we use our equation for a wave, V equals F lambda, that comes up a lot, we can write that the frequency is equal to the velocity over the wavelength, and in this case, the wavelength is equal to 4L. So the frequency, which is the fundamental frequency in this case, is equal to V over 4L. Okay, now let's consider what's the next harmonic. So once again, if this is a closed pipe and we're going to have a harmonic, we have to have an antinode at this end and a node at this end. The next way we can achieve this is by having 3/4 of a wavelength inside this pipe, as shown in this diagram here. So in this case, L is equal to 3/4 lambda. And so once again, we can do the same maths, and we can write that the frequency in this case is equal to 3V on 4L. So this one is actually known as the third harmonic. So in a pipe which is open at one end and closed at the other, we don't actually have any second harmonic. We go from the first harmonic, or the fundamental, to the third harmonic. We'll see why we give them those names in just a minute. Let's just consider one more harmonic now so that we can clearly see the pattern which is emerging. Okay, so antinode here, node here. The next option we can have is 5/4 of a wavelength inside the pipe, in which case the length of the pipe is equal to 5 lambda on 4. And so the frequency for this harmonic is equal to 5V over 4L. So hopefully you can now start to see the pattern. The frequencies for the harmonics are given by Fn, so the frequency of the nth harmonic is equal to n times V over 4L, where V represents the speed of the wave through the pipe. So in this case, it's the speed of sound in air. As with standing waves on strings, the harmonic frequencies are all integer multiples of the fundamental frequency. So this is why we call our harmonics the first, third, fifth, seventh, ninth, etc. So that we can have the ninth harmonic being 9 times, having the frequency which is 9 times that fundamental frequency. So now let's consider a pipe which is open at both ends. When a pipe's open at an end, then we end up with an antinode at that open end. So in this case, the fundamental frequency has an antinode here, an antinode here, so we'll need a node in the middle. So looking at the figure, you can see a quarter wavelength and then another quarter wavelength. So we've got half a wavelength inside that pipe there. So L is equal to lambda over 2, and then just using the frequency is equal to the velocity of the wavelength, we can see that the frequency is equal to the velocity divided by 2L in this case. The next harmonic will be when we've got a antinode here and here, and we actually have a full wavelength inside the pipe as shown in this figure here. So in this case, the length of the pipe is equal to the wavelength and the frequency is equal to V over L, or we could write this as 2V over 2L if we wanted. Mathematically, those are the same thing, and in a minute we'll see why it could be useful to write it that way. Okay, and then the third harmonic is when we have 3 half wavelengths inside this pipe as shown in this final figure, and in this case the length of the pipe is equal to 3 half wavelengths, and so the frequency of this third harmonic is equal to 3V over 2L. So hopefully now you're starting to see the pattern. If we wanted to find the nth harmonic in a pipe open at both ends, we'd have Fn is equal to n times V over 2L. Okay, so now that you've been introduced to that, let's use it to try and solve some problems.